Welcome back, folks. We are moving on with chapter 6, or to section 6.4, and we are going to be introduced to logarithms. Logarithms are the inverse of exponential functions. And so let's talk about them a little bit. Logarithmic functions and exponential form versus logarithmic form. So I want to impress upon you how important this is. So if I have this, y equals a to the x power, the opposite way to write that is going to be x equals log base a, that's a subscript, of y. Now you'll need to study exactly this. And what I mean by that is, this is, a is the base, it goes down here. The exponent becomes the part by itself on one side. And the part that was by itself before is now the domain of the logarithm. So you can see everything's kind of flipped around. And so let's go through some concepts that have to do with logarithms. First of all, f of x equals b to the x power is 1-to-1, so it has an inverse. Exponential functions are always 1-to-1. This is sort of a derivation on how to get to a logarithm. Now the domain of f is -infinity to infinity, meaning x can be any value in the whole world with an exponential function. And the domain of f inverse here's what it should say. Domain of f is the range of f inverse. So meaning everything switches. And the range of f is the domain of f inverse. So the domain of f, which is -infinity to infinity, is the same as the range of f inverse. So this is also -infinity to infinity. The range of f is 0 to infinity. So the domain of f inverse is also 0 to infinity. And we'll see what that reflects like when we get to the graphs. All right, so I want to use this form here. And we'll start here. Here's exponential form. So 2 to the third power equals 8. That's a true statement. Nothing wrong with that. If I want to rearrange it into logarithmic form, then it's going to be that 3 is equal to log base 2 of 8. Now you could put log base 2 of 8 equals 3. That's the same statement. It really just depends. All right, let's do a few more. So 5 to the -2nd power is 1/25. That is, of course, a true statement. Rearranging this, we get that -2 is equal to log base 5 of 1/25. And b to the first is b, which means that log base b of b is equal to 1. And b to the 0 power is 1, which means log base b of 1 is 0. So it's just sort of different ways of rearranging. And we'll come back to this when we get to the section with solving equations and things like that. So this is a very useful piece of information. Part 2, the common log and natural log. Now what I want to do is show you on a calculator. This is what's called the common log. I'll get to that in a second. This is the natural log. Most calculators only have common log and natural log. So let's talk about what that means. The natural log is base e. It's that weird number e that we talked about before, that 2.7. In fact, I want to show you how to get that on your calculator. You can see the e is above the ln button here. So to activate that, what I'll need to do is I will need to hit second first. So second e to the first power. So there's our 2.71828 and so on. This is what's called a transcendental number. It's a irrational number, meaning it goes on forever and ever without a pattern. It's like pi. And when we have log base e, we never write it that way. We always write it as ln. The French got to that before we did. So it's instead of natural log, it's logarithmic natural, however you would say that in French. Log base 10 is the common log. And we don't write in the 10. Every other base we write in, except for the common log and the natural log. So common logs would be used for things back when we used to have the Richter scale. They would use it for pH levels. So a pH level of 7 is pure water, and so on. The natural log, actually, we use all the time in calculus. Like we never use a common log or any other base. It's just much easier. The number e makes the calculus world a whole lot easier. And so here is back and forth between the two things that I mentioned up here. And because they're inverses of one another, when you composite them together, they should get x every time. So same here, we get x. So let's go through some of these examples. Let's pick another color. So log base 3 of x. And so we are using, let me write it out because I don't, yes, right here. So this is the one that we're using here. So when you have the same bases like that, the exponent is just, it's like the log and the bases and everything just kind of cancel out. So this log base 3 of 3 to the x is just x. Now the natural log is base e. So this just becomes 7. So we know this is the common log here because there's no base. So log base 10 of 10 is just 1 times 9. So this is just 9. Now we're here. And we can see that the bases are the same. So we just get an x back out of that. E and ln are base e. So this is just 6. And I mix that up. That should be a 4 there. And 9 there. So the answer is just 9. All right, page 2. Graphing logarithmic functions. Because these are inverses of one another, I mentioned this in a previous video. If we take the line y equals x, and we go right down the middle here. So if we go right down y equals x route. So this is y equals x. And we do a logarithmic function. It's going to look like this. Or let's do the, we'll do this one first. Number crosses at 1. Supposed to cross at 2 there too. Then the inverse of that is going to look like this. It's going to cross at 1. Going to get closer and closer. And you can see it makes it symmetric about the line y equals x, like a mirror image almost. Had I drawn those better. Now this is when b is positive. B is 2 in this case. They're all going to be positive. B has to be positive, but bigger than 1. Now if it's between 0 and 1, then we're going to have a problem. Not a problem, but it's going to go in the opposite direction here. So let's do our y equals x again. Y equals x. And so now when we have a base like this, our exponential function does this. Crosses at 1. It gets closer and closer and closer to the x-axis while it kind of explodes this way. And the other one does this. So it's going to cross at 1 here. It's asymptotic there. And you can see it makes a mirror image on both sides as we look at that. Kind of beautiful, actually. No, my drawings are all like great, but they would be beautiful. All right, so now let's see what this looks like individually. So I'm going to draw these out individually so we get a better idea of what we're looking at here. And here we go. This one here is going to cross 1. So it's asymptotic to the y-axis here. And to be clear, the domain in this case is 0 to infinity. Right, so it's never going to hit 0. It's always going to get closer and closer. So it's 0 and infinity. The range is negative infinity to infinity. Now, if we draw the green one from above, this is going to cross here, asymptotic here, there. The domain and range are still the same. And you'll note that they're exactly the opposite for exponential functions. All right, let's talk domain of logarithms. This is not particularly difficult. So the domain, meaning what x values am I allowed to use? It has to be positive values only. In fact, let me show you in a calculator real quick what that looks like. So if I do log of 5, that's fine. We get some crazy decimal. But if I do log of 0, nope, not in the domain. We have an error. So you can see 0 is not included. So let's do these. And basically, what we're going to say about this is that 2x plus 3 has to be strictly larger than 0. So x has to be bigger than 3/2. So the domain for this particular function is going to be negative 3/2 to infinity. Part B. So x squared minus 4, again, has to strictly be bigger than 0. Now we can see this factors, difference of squares. And so we're going to have to test the regions. You know what? We know that this is a parabola and its Lie coefficient is positive. So in reality, this graph is going to look like this. It's going to be here, it's come down, go back like that. So since we want the positive versions only, the domain in this case is going to be negative infinity to negative 2, union with 2 to infinity. So we can see it's positive up here, positive over here, but it's negative down there. So here's our domain. All right, let's see. And notice it doesn't matter what the base is. So this one, 2x minus 1 has to be bigger than 0. So x has to be bigger than 1/2. No problem. However, part D is a little more work for that one. This means that x plus 1 over x minus 2 has to strictly be larger than 0. We know 2 is not in the domain. But again, we're going to have to do one of these. And we're going to have to actually test points. So we have -1 as a critical value, and we have 2 as a critical value. The way I showed you how to do this was partition it up like this. And let's test something on this side. Let's test x equals -2. So -2 plus 1 over -2 minus 2. It gives us -1 over -4, which is 1/4. The point is, it's positive. For the middle part, zero's in there, so let's test 0. X equals 0. So 0 plus 1 over 0 minus 2 is negative 1/2. The point is the sign is negative. And let's test a point over here. Now let's test x equals 3. 3 plus 1 over 3 minus 2. That gives 4 over 1, which is 4. And again, the point is, where is it? Positive. So our domain for this one is going to be negative infinity to 1/4. Not 1/4, to negative 1. Start again. Negative infinity to negative 1. Union with 2 and on. Welcome to logarithms. They're new, they're different. Hopefully we can get kind of used to them.